بسم الله الرحمن الرحيم. رب اشرح لي صدري ويسر لي امري واحلل عقدة من لساني يفقهوا قولي. الفيديو ده هيفضل لفترات طويلة، هفضل افتحه واتفرج عليه كل مرة عشان افتكر الحدث الجميل اللي جه من boys of grade 11 2019 first semester, and we will back inshallah in 2031. Bismillah ar-Rahman ar-Rahim. The second part of the learning outcome 6, it's talking about the chemical equilibrium. And we stop at the factors affecting the speed of the chemical reaction. But before this, we are going to talk about the chemical equilibrium constant, or the Kc. Kc represents the ratio between the concentration of product divided the concentration of the reactant. Like when you're talking about any experiment or any example, like H2 react with I2, giving to us 2HI. Gas, and gas. In this case, if we need to determine the value of the Kc, we will find the concentration of the product, Hi, raised to its power, divided the concentration of the reactant, the hydrogen, multiply the concentration of the iodine. H1 raised to its power. What's meant by the power in this case? It means that the balancing of equation. So returning back to the type of the chemical reactions. Types of chemical reactions. And graphs. Maybe you will find the complete reaction. May be reversible. In the complete reactions, we'll find the one of the product. Maybe talking about the complete reactions like NaNO3 or AgNO3 plus NaCl, the aqueous solution. In this case, we'll find that the complete reactions move only in one direction, the direction of formation of product. So it will be NaNO3 aqueous, AgCl as a solid substance. In this case, we'll find one of the products are out from the reaction as a BBT, maybe escape from the reaction in the form of the gas, in form of gas. So we can call the complete reactions. Products are produced in form of the solid, one of the product in the form of the solid, one of the product escape from the reaction as a gas, like the reaction of the nitrogen plus hydrogen. It is a complete reaction because we will find gas, and the product NH3 gas. So we can say that the complete reactions, the product are produced in the form of the solid or one escape in the form of the gas. I want to represent it in the graph. Representing it in the graph is talking about the concentration and the time. For these reactions or for any reactions, let's talking about the reaction of N2 plus 3H2 giving to us 2NH3. In this case, we will find the reactant decreases concentration till it becomes 0, and the product concentration start to increase. This is the product and this is the reactant. We will find in the one of the period of the time, the graph, it represented by straight line. This is straight line, it's called the equilibrium position. What's meant by equilibrium position? The point at which the concentration of the reactant and the product not change. It's become constant. So it will be represented by straight line parallel to the time axis or the x-axis. A point at which the concentration of the reactant or the product become parallel or the constant is called the equilibrium point or equilibrium position. But in the case of the reversible reactions, let's talk about one of the reversible reactions. It is the gaseous reactions. But if we put this gaseous reaction in closed container, in this case, we can say that is a reversible reaction. Since the reversible reactions, both the reactant and the product are found in the medium of the reactions. No one escapes from the reactions. Maybe sometimes the concentration of product equal the concentration of the reactant. Maybe product concentrations greater than the reactant concentration. Maybe the reactant concentration greater than the product concentration. I need to represent them in the curves. In the case of the product, equal the reactant concentration. So we'll find the concentration and the time. We'll find the product concentration decreases and the reactant concentration decrease and the product concentrations increase till they reach the same point. In this point, we will find the value of the Kc equal 1, since Kc represented the product over the reactant. So 5 over 5, it will be 1. Representing the curve between the concentration and the time. When the product is greater than the reactant, product increase, reactant decreases. In this case, we will find the reactant not reaches the zero. It's not a complete reaction. So this point represented the equilibrium position. But in the case of the reactant is greater than the product, so we'll find that reactant decreases and the product increase. But in this point, the concentration of the reactant is still greater than the concentration of the product. As what? As the example of the nitrogen gas with the hydrogen. Let's represent it by the graph. All of this I will clean it. For the reaction of the nitrogen with the hydrogen, giving to us 2NH3. Sorry. Between the concentration and the time for each reactant and the product, we will find the nitrogen concentration will decrease, but will not reach the zero. In this case, we represented the reversible reactions in the closed container. Closed container. Container, okay? So in this case, it represented the nitrogen. What about the hydrogen? The hydrogen else, it's become to decrease. Hydrogen type. What about the ammonia? The ammonia, it will increase, but the rate of the ammonia is less than the concentration of the hydrogen. The hydrogen concentration 3 moles and the ammonia 2 moles. But so we'll find in this case the concentration of one of the product or one of the reactant greater than the concentration of the product. What is the factor affecting the speed of the chemical reactions? Returning back to the scientist, it's called the Le Chatelet. Le Chatelet principle said that when one of the following factors as concentration, pressure, even temperature, affect reaction at equilibrium, reaction shifted toward the direction which neglect or decrease this factor. Let's explain it. One of the factors affecting the reaction at equilibrium, maybe concentration, maybe pressure, maybe the temperature. We are going to talk about them according to the examples. In this time, we'll find the reaction shifted toward the direction which neglect or decrease these factors. Let's give an example. For these reactions, N2O4, nitrogen tetroxide, inside the closed container. This is have a pale brown color, lighty brown, and when I have NO2, nitrogen dioxide, reddish brown color. Inside the closed container, both inside crushed ice, we'll find that the nitrogen tetroxide are formed, but same container is added to hot water. Heating, we'll find NO2, it will form it. Heating, cooling. By heating process, we will find the reaction shift. When we increase the heat, increasing the temperature, the reaction shifted toward the formation of NO2. But by cooling, we will find the reaction, our molecule, it will be collected to forming nitrogen tetroxide. So the first one, it is the factors affecting the temperature. It's talking about the concentration. These reactions, NH4, SCN, ammonium thiocyanate, react with the iron trichloride, FeCl3, iron trichloride. Iron trichloride pale yellow, giving to us FeSCN, all three, iron tricyanate, plus NH4Cl3, 3. In this case, what is the effect of the concentration? If we adding excess amount from ammonium chloride, we will find the reaction shifted toward the formation of ammonium thiocyanate. We can have a forward and backward. If we adding NH4Cl, it means that increasing the concentration of ammonium chloride, so the reaction must be back again toward the reactant, to away from the excess concentration of ammonium chloride. But what's happened? If we add an excess FeCl3, we will find the reaction shifted away from the reactant direction toward the product direction. Reactant direction, it's mean backward. Product direction, it's mean forward. So we have reactant and product in this reaction, forward and backward. Adding ammonium chloride, away from ammonium chloride that is found in the product, back, so we return back to the reactant. Adding the iron trichloride, it's making the reaction shifted forward, away from iron trichloride. It is the second factor, it's called the concentration. What is about the pressure? Then we are going to talk about the endothermic and exothermic reaction. The third factor is talk about the pressure. Pressure. Increasing pressure mean decrease the volume of container. Decreasing pressure mean increase volume of container. For these reactions, the reaction shifted forward or backward when we increase the pressure. To find if the reaction shifted forward or backward, firstly, count the number of molecules or number of moles. 1 and 3 when I have 4 moles. For this, when I have 2 moles. Increasing pressure or decreasing the volume of container, it will shift the reaction toward the less volume. So when I have 4 moles and this 2 moles. So by increasing the pressure, we'll find the reaction shifted forward toward the less volume type. What's happened if we decreasing the pressure? Decreasing pressure. When we decreasing the pressure, it means the container volume, it will increase. Decreasing the pressure, we will find the reaction shifted toward the more number of moles, the more number of molecules. So in this case, shifted from the 2 toward the 4. Endothermic and exothermic reaction, return back to it. I want if when I have an exothermic reaction or endothermic reaction, at which direction we will shift the reaction according to the Le Chatelier principle. Exothermic reaction endothermic reaction. In case of the exothermic reaction, we will find the reactant gives product plus heat. Endothermic reaction, we will find reactant plus heat gives the product. The delta H for the exothermic reaction, negative value. Delta H for the endothermic reaction is a positive value. The shape of the graph for exo we'll find like this. Reactant, product, the energy of the product less than the energy of the reactant. This is state, it's called that transition state or activated complex. Activated complex. In this case, we'll find the value of activation energy, EA, from what the reactions, our reactant again. The activation energy represented from the reactant toward the activated complex. What's meant by the activated complex? It is a state at which all the reactant reach it before end toward the product. It represented like when we reach the activated complex, like the sliding game. You must up the stairs to the top of the sliding game, then we'll slide toward the product. But all the reactant must reach the activated complex. What's meant by the activated complex? Transition state between the reactant and the product. In endothermic, we'll find the reaction taking another energy of the reactions and passing the time. We'll find an endothermic reaction, the reaction will be like this. What is the value of the activated complex? Reactant and product. Activated complex represents this. EA, activation energy, and this is called the activated complex. The reaction shifted forward or backward when we're talking about the exothermic reaction. Exothermic reaction, like the reaction carbon and the oxygen, giving to us carbon dioxide gas. Inside the closed container, it will be reversible reactions. Hydrogen plus iodine, giving to us 2 hydrogen iodide or hydrogen iodide gas. Endo BAF. Increase, decrease. Exo fab. Increase or decrease. So in this case, in the endothermic reactions, increasing the temperatures, it will shift us forward directions. Decreasing the temperature, it will shift us backward. Exothermic, increasing the temperature, shift the direction backward. Decreasing, shift the direction forward. Take an example. For this reaction, it is the endo. If we increasing the temperature, at which side the reaction's temperature is found, we'll find heat in this direction. By increasing the temperature, you must away from the side of the temperature. So you will shift it forward. Go away, forward. But what's happened if we decreasing the temperature? Decreasing the temperature, we must return back to the heat again. So it will be shifted backward. But for the exothermic, if we increasing the temperature, at which side we will find the temperature or the heat energy? In this side. Increasing the temperature, making us away from it, returning backward. Type. If we decreasing the temperature, it making the reaction shifted forward. This is according to the Chatelet principle and the factors affecting the Chatelet principle. Let's talking about what is the effect of the catalyst for the reaction at equilibrium. Catalyst, in this case, it's only decreasing the activation energy. It's not affecting the equilibrium position. If we add, this is the transition state without adding the catalyst. But if we add the catalyst, we will find the activation energy will decrease. Activation energy from the reactant toward the product, it will decrease. It is the effect of adding catalyst. But the question now, catalyst affect the equilibrium? No, the catalyst only affect the activation energy, not affected the equilibrium constant or the equilibrium position. When I'm talking to you, what is the effect of the catalyst when we add the catalyst to a reaction at equilibrium? We said only nothing. The forward direction equal the backward direction, since the catalyst only affect the equilibrium, not affect the equilibrium, but affect the activation energy. We needed to talk about some activated process in industrial, so we are going to talk about the activation of the catalyst during our catalyst, the role of the catalyst in the ammonia industry, and the contact method. If we're talking about the chemical reactions, talk about what is the effect of the catalyst, like the contact method, and the hop push. Contact method, it means the reaction between sulfur and oxygen, giving to us sulfur dioxide. Sulfur dioxide react with an excess oxygen, giving SO3. SO3 reacting with the water, giving sulfuric acid. The last equations, it represents the catalyzed reactions. We adding the vanadium pentoxide as a catalyst and 450 degrees Celsius. In this process, we will find the catalyst allows the reactant SO3 and the water vapor to contact in this in its surface. So the catalyst represents like the carpet, and over this carpet we will find the sulfur trioxide and the high water vapor contact over the surface of the catalyst. Hopper push represents the preparation of the ammonia, nitrogen plus the hydrogen, to giving to us ammonia gas. This reaction can taking place if we return back to the Zondel. We'll find that when having a triple covalent bond between the nitrogen molecules and the single covalent bond between the hydrogen molecule, strong bonds, there is not broken easily. In this case, we need the high pressure equal 500 atmospheric pressure and 500 degrees Celsius. The catalyst iron. The catalyst over its surface, it represents the taking the bond between the nitrogen, make it the single nitrogen atom and the single nitrogen atom, and breaking the bonds between the hydrogen atoms, hydrogen, 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 3 molecules, hydrogen and the hydrogen. Then each nitrogen atom surrounded by 3 hydrogen over the surface of the catalyst, and another nitrogen atom surrounded by 3 hydrogen atom over the surface of the catalyst. It means not like the adsorption process. It means the catalyst represent like the surface, make the reactant able to react with it. It's what is the difference by absorption and adsorptions? Absorption like that you have a sponge, and the sponge absorbs the things inside it. But adsorption, it means that it's collect over its surface. The last thing, the ionic equilibrium. Ionic equilibrium is talking that the established case of equilibrium between the weak electrolyte and the ions produced from it. Then we're talking about the rules for this chapters or learning outcome. Ionic equilibrium. Okay, talking about it only, since there's coherence between the topics. Ionic equilibrium represents the equilibrium between the weak electrolyte and ions produced from it. It is our topic, inshallah, in the next learning outcome 7. See you soon, inshallah.